Hello everyone, this is Zheng Yuanzhu.
This is Haiqi. Today we will be presenting our final project, a visual storytelling system based on hard example selection. We'll talk about our project from 6 sections: introduction, problem formation, problem solution, model architecture, experiments, and conclusion. Our goal is to build a model that can automatically generate a human-like story based on a visual scenario, in our case, images. This is a multi-modal challenge in both natural language processing and computer vision. Here is an example. Our goal is to take a sequence of images as input and output the corresponding text and giving a whole story. Next is problem formation. So in our problem, we are considering the task of visual storytelling where the input is a photo stream of 5 ordered images, and the objective is to output 5 story sequences. Each story sequence includes a number of words that belong to a fixed known dictionary. We conduct our experiments based on visual storytelling VIST dataset for sequential vision to language. The dataset includes 80,000 unique photos in 20,000 sequences, aligned to descriptive and story language. Below are a sequence of 5 images along with their corresponding texts. At the training stage, we will feed the model with both images and their corresponding texts. While at the inference stage, the model will only take the images as input and output the story language. We face some challenges here. The generated stories contain an overwhelming number of boring sentences and unrecognizable patterns, such as we had a lot of fun, we had a great time, etc.
The next is the problem solution. To solve the problem above, we tried to use the online scheduled hard example selection, OSHIS algorithm. So the basic idea is to automatically select those improperly generated stories in a reasonable decay ratio that to make the training more effective and efficient. There are 2 points. The first is to reduce the focus on the easy examples, like was very happy, and those examples are often appear in the training stage. And second, to enhance the effect by focusing on the hard examples. As you can see, in the formula below, we first calculate the losses between the ground truth and the generated text, along with the R ratio, and then mask the easy examples and together with the original loss as a new loss. The pseudocode here explains how our algorithm works. Then we explore 3 different decay schemes, which are linear decay, exponential decay, and inverse sigmoid decay. We tried the 3 different decay schemes to try to improve the performance without affecting the convergence of the model through different scheduled decay. In the right side, the figure shows that how the scheduled ratio changes along with the epochs. By the way, the decay ratio is defined by the threshold T and parameter K. Essentially, the scheduled decay ratio alpha defines how sensitive the model to the easy examples. And then is our model structure. Our model contains 3 components. The first is a visual encoder, and then is the storytelling decoder, and our online scheduled hard example selection algorithm. So for the model, first, the encoder takes a photo stream as input, and then encode the photo stream to images features, and then set the feature to the GRU. And GRU further encode the features and then send the features to the storytelling decoder. The decoder is a vanilla single layer GRU, and the decoder can predict the word one by one. We compare the predicted word and the ground truth and calculate their loss and send the loss to our online scheduled hard example selection model. So in our model, we first sort all the losses values, and then we mask the easy examples and combine with the hard examples to calculate the new loss. The next is our experiment. So first, we compare our model with the state-of-the-art systems on 4 matrices. They're blue 1, 2, 3, 4, and Meteor and Roge-L and Cider. We have 5 baselines, and then we try the linear decay, exponential decay, and the inverse sigmoid decay. And we find that the exponential decay has the best performance if we set the parameters properly, which means you just need to slightly change how the model trains that can improve the performance slightly. And we also explore the effect of the different scheduled decay ratio schemes. Here we set different t and different k here. We performed a bunch of experiments to explore which parameter setting is the best for the VIST dataset. And then we explored the effect of the fixed schedule decay ratio, and we find that we set the 0.9 is the best, and we'll also find when to start using the Osh's algorithm is the best. If we begin to use Osh's algorithm at the 5 epoch, it will perform the best.
Here's our conclusion. We introduce a subtle and effective Osh's algorithm for visual storytelling tasks. Osh's algorithm makes the model dynamically more sensitive to focus on predictable examples by automatically selecting hard examples in a scheduled decay ratio. We conducted extensive experimental analysis to demonstrate the effectiveness of the proposed algorithm. It leads to the state-of-art results in this dataset on standard benchmarks. Osh's is an out-of-the-box algorithm that can be plugged into any existing model for sequence generation tasks to further boost the performance. Future work will explore the application of Osh's algorithm in other fields. That's all. Thank you.